so I guess I should start by saying that George just looked at an overlooked problem. So I was asked to look at a very overexposed problem, which is about changes in the overturning circulation, especially those due to anthropogenic sources. And I guess I've changed the title slightly because this was supposed to be about abrupt climate. So I've added, are there any abrupt surprises? I think also I've probably disappointed George that I used to do, simpler models of El Nino and whatever, but I'm afraid in the last 10 years, George, I've got into climate models and I've sunk my head's underwater, and I'm not going to come up anytime soon. I'm involved with the Community Climate System Model, the CCSM, which is run from NCAR and elsewhere. My name's up here, but many of these results are from other people who I won't have given any acknowledgements to, but believe me, a whole bunch of people are involved in this. So we always start off, and I'm going to do the same thing, by talking about the strength of the maximum of the overturning circulation in the North Atlantic Ocean, which I've labeled here as anywhere between 14 and 26 fedrops. Just for clarification for people who aren't quite so familiar with this, how strong is 20 fedrops, for instance? Well, the transport of the Florida Straits is somewhere on the order of 27 to 30 spherops. The Gulf Stream, farther north, is a lot stronger than that. Different estimates, but we maybe say anywhere around 70. As was very nicely just illustrated, quite a lot of that goes round and round. Quite a lot of that goes up and down. So of that 70, quite a lot, percentage of it, goes round and round. And what the MOC represents is an integral across the Atlantic of the water that's going up and down. So if water is going north, right in the surface in the west, and going back east, south in the east, that doesn't count to the MOC. So that's what you look at as the horizontal circulation. The overturning circulation is what really goes up and down, but it's a zonal integral. In reality, the vast majority of that returns as the deep western boundary current under the Gulf Stream. So what's the best estimate from any observations or whatever that we should have of this number? But
that number has two components.
Yep. Do you want to go further than that?
Spend 40 minutes doing
The best estimates we have are somewhere from observations that are somewhere in the region of 15 to 20. Some people will say 17 is our best number. 20 is a bit high. So there we go. So the first thing I wanted to do was say these are some present-day control runs with 3 different versions of the model with different resolutions. While the T's here refer to the atmospheric resolution. This is about 1.5 degrees. This is closer to 3. This is more like 4 degrees. And the ocean side, we have a 1 degree model and something like a 3 degree model. Actually, the 1 degree, it's 1 degree in the zonal, in the meridional direction. It has varying resolution with much finer resolution at the equator to represent equatorial processes, coarser resolution farther north, but the average resolution in the meridional direction is about 0.6. So we do a present-day control run, runs out for several hundred years, and these are the results we get for the overturning circulation. And as you can see, the strength of that overturning circulation is monotonically increasing with increasing resolution in the model. So that's one thing to bear in mind when I talk about these results, is that if we take the limit, we're going to go much higher than we should. The reasons for that is that the winds get stronger as your atmospheric component gets more resolution. And the other one is that you actually resolve the topography better, and that allows more return circulations around the topography. The other thing to note is that in the present day climate, you get oscillations that are on the order of 6 or 7 sphere drops compared to a mean of something like 22. So, pardon?
Does everybody know what a sphere drop is? It's a lot of
Does anybody not know what a sphere drop is?
That's a loaded question.
It's 10 to the 6 cubic meters of water per second. Okay? So there's a lot of variability. So I think, what you've got to keep in mind here is that when you look at these model results, you have to do so with a reasonable amount of skepticism.
Is there a fixed latitude which this is defined?
This is the maximum throughout the North Atlantic.
So does it move latitudinally with resolution?
It moves slightly with resolution.
Slightly.
Yeah, north and south with resolution.
Where is it occurring?
This occurs around 40, somewhere between 35 and 40. So, just to expand a little on the discussion we just had between what is thermohaline and what is overturning circulation, I wrote a paper on whether the thermohaline circulation declines in the next century, and I didn't like this measure of the total overturning as a measure. I wanted a measure of the deep water formation regions, because the deep water is formed in the Greenland, Icelandic, Norwegian seas and in the Labrador Sea. A lot comes over the Denmark Strait. So instead of looking at this general measure, I looked at the measure of the amount of water that comes over those straits and sinks deeply to form North Atlantic deep water. In the models, that number is actually more like 5 sphere drops. So if you think of the deep water formations as what the thermohaline should do, the amount of water involved in that is about 5. These numbers for the overturning circulation are more like 17 in the models, more like 20 to 25.
What's the heat flux?
The heat flux.
Isn't that what you would care about? Is the radionic flux of heat? Because in some sense, you don't care about the mass flux.
Right. The other thing about this overturning circulation, of course, is it transports heat northwards in the Atlantic. 24 north in the Atlantic, it has its maximum heat flux of something like, best estimates, 1.2 petawatts. That's as much as the atmosphere is doing at that latitude in the north. And as you go farther north, that heat transport goes down dramatically, but there's debates about whether is it the wind circulation that's doing the majority of that, or is it this deep water formation at high latitudes. Now, interestingly, of course, nobody's taken any notice of my paper, and of course, so everybody
Submitted to Science and Nature.
No, it wasn't, because it wasn't interesting enough for Science and Nature. but nobody's taken any notice of it whatsoever. So every figure that's ever produced about this still has this number, this total North Atlantic overturning circulation, and I will follow that and just talk about it.
I was trying to make a serious point. In terms of the climate system, it's the heat flux of the North Atlantic that you would think is going to affect the atmosphere. And I guess it's a question: does it vary monotonically with resolution the same way the mass flux?
Oh, not as much. Not as much. The ocean. Its northward heat transport varies a little and goes up a little, but not nearly as much in proportion. So that says you're changing the temperature distributions so that with a different circulation, different temperature distributions, you are transporting northwards a similar amount of water.
Why this focus on the mass flux when the atmosphere would care about the heat flux? Mm-hmm. It just seems like a rather odd point of view. Because if the heat flux were stable, you might say, okay, you've got it right. It's no longer sensitive to resolution.
So if we go on at this rate, this is my first slide. So let's go. Let's go. Let's have at least. Let's have at least one more before we stop. So, our group, like many others, says then, what's this? I've switched now from the title head MOC. Here I've said THC. I'll use those sort of interchangeably. What's the response to increase in CO2? So here, again with the 3 resolutions, we have a control run. Then we have one of these standard runs where you increase CO2 1% per year. That doubles CO2 in 70 years. It quadruples it in 140 years. The green is then what happens when you keep CO2 constant at twice the value. And blue, I guess the tent's falling down now. And the blue is what happens when you keep it at 4 times CO2. And the general result is that the MOC weakens as you're increasing CO2. Then it starts to recover slowly as you keep CO2 constant at twice or 4 times its level. And interestingly, this is why I said this comment this morning about in Klaus's talk, the absolute magnitude of the decreases are different in the different resolutions, but the percentages are in fact about the same. So that's a sort of interesting point. But for a 4 times CO2 world, you've gone in this one from about 23 down to about 15 or 16, and then it starts to recover. So it's gone down by about 1/3. Now, in my definition, that is not a collapse. I think we... heat transport goes down again and then starts to recover in proportion to these. So the ocean heat transport goes down not quite as strongly as these, again, just as the difference wasn't between them, but it does go down in a warming scenario. So for 4 times CO2, as it's increased, the thermohaline circulation goes down to about 2/3 of its present day, is what this model says, and then will slowly increase. Oh, I thought I was going to get away with that.
Is there climate sensitivity attached to those numbers?
There is. What exactly do you mean by climate sensitivity? There's certainly a sensitivity on...
The warming.
Right. This will depend on many things in your couple model. In particular, the effects will be due more strongly if your climate sensitivity is stronger. Now, in my view, climate sensitivity is actually set mostly in the atmospheric component and in its cloud parameterizations, not particularly in its ocean component.
But the question is, what is the equilibrium response of CCSM to the doubling of CO2 long term? How does it relate to uncertainty?
That also depends on resolution. 2.7, 2.5, 2.3.
Okay.
Okay. So
can we just why don't you have the same climate sensitivity for?
Because exactly what I've said before is that the climate sensitivity depends on your cloud parameterizations, and they affect the simulation differently depending on your atmospheric resolution.
And you're getting different results for different atmospheric resolutions with the different parameters.
With nominally the same parameterizations. But that's one of the reasons that if you change your parameterization, you'll change your climate sensitivity. And climate sensitivity across the range of climate models varies by a factor of 3. 2.7 to 2.3 is below the mean. It's on the lowish side. Okay?
There's no real change in a 1% per year increase.
Sorry, I'm not sure.
There's no change in the overturn.
Yeah, these are what they were. No, back. The red and the cayenne. The red and the cayenne are 2 members of an ensemble. Yeah, so that is the steady increase and then recovers afterwards. Okay, these are the future scenario runs that we've done to submit to the IPCC. What you do is an 1870 control run, then you do an ensemble of runs to try and reproduce the conditions between 1870 and 2000. So it's not just paleo where you have data to try and compare. You do have some data between 1870 and 2000. Then we've done runs where you keep the CO2 level at its 2000 value. Those are called commitment runs. Then there's a B1 stabilization, gets it up to about 550 from present day 275. Then there's a much bigger increase, A1B, up to 750. And interestingly, at the simulator in Japan, they've run some where they follow this A1B to here, 2150, and then they bring it down over 100 years to the B1 stabilization. So those are the runs we've done. These are the responses of the North Atlantic MOC to those runs. Point out again, a lot of variability during the 20th century for these. These are now all for one resolution. The various colors are for ensemble members, different ensemble members, using the same scenarios. So, in the B1, it declines.
How they differ?
Yep, they are started at different years, different times from the 1870 control run.
But I mean, the difference between the red one and the blue one is relatively strong. No, I mean in 1930 or 1940 or so.
Yeah.
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 So they essentially differ by 1 year or something, that's all? The initial conditions?
No, by 20 years from the 1870 control.
20 years.
Right. So what happens is, as I said in the control, you have a large oscillation in the overturning. So depending on where you start it from, gives a sensitivity of what value you'll get and where that oscillation will be. That's natural variability tying into how you do these future scenarios. So, there's not a whole amount of variability among the ensembles, but there's some. So for the one that goes to 750, you go down to 16.5 from 22. So that's a 25% decrease. Then they start to recover as you go through the times. And the interesting one here is that the one where you go with the stabilization, the overturning recovers more quickly, and in fact is stronger again than the 551 that you've gone back to. If you go back to that last slide, what happens is the surface temperatures in the atmosphere respond fairly quickly from the values appropriate for here to the values for here. The overturning, as you come down here, gets faster than this value here. So what you're doing there is, over time, you've put heat into the operation, it's heating up, and that has reduced has increased the stability of the column. Now you've got to a situation where you've put heat into a lot of the operation, then you start cooling it again because the scenario has gone down, and that then produces more unstable conditions in the surface. And that produces more overturning than the other scenario. Incidentally, in this committed climate change here, you don't get very large increases in surface atmospheric temperature. It's about 0.5 degree at 2100. Where you do get continuing large increases is actually in sea level, because throughout this time, you're still pumping heat into the ocean at a rate. So in this commitment, you have a large commitment to sea level rise, not that much more commitment to temperature rise. Well, that's an interesting point. Carry on. So here is the sea level response, for instance, in the overshoot scenarios. So here you've gone from the A1B, which is going up at this sort of level. The less fast increase, B1 does this, but in the overshoot scenario, the temperatures would go back to these figures very quickly. But in the overshoot scenario, you do not in sea level because that heat is already in the ocean. So you've already heated the ocean up due to, this is sea level rise just to thermal expansion. There are 4 components to sea level rise: thermal expansion, different currents, fresh water, added fresh water in, and changes in the land level. Any other questions on sea level, go to the expert in the back of the room. This is just the globally averaged increase due to the ocean getting warmer. And yes. Okay.
So there's no ice sheet coupled to that.
There's no ice sheet coupled to that. So we do not do any predictions about the increased level due to extra fresh water.
And also no prediction about the effect of ice sheet melting on salt fluxes in the Atlantic.
That's correct. And before you, the sharp-eyed of you will say that, in fact, this is actually wrong because there's actually a decrease in sea level over this century, which is not correct. And what's not been done here is actually you haven't taken out a trend from the control run. These runs get balanced, and you do it the best you can at the top of the atmosphere. This one actually was really well balanced for the present day control. It was about 0.2 watts. When we then did the 1870 control, that balance got worse. It went to half a watt per square meter out of the top of the atmosphere, which said we did that actually wrong. But that half watt out of the top of the atmosphere over this length of time is actually coming out of the ocean. So the ocean is losing heat so that the control run has a downward trend of sea level. And if you're going to do these figures, you should actually subtract that deviation from the control run from these. So these actually should go up by on the order of 10 or so centimeters. The scale here is 0 to 60 centimeters. Michael?
I'm just wondering if there's a contribution from net salinity input or output of the ocean as well. So you just said net input of heat or loss of heat.
This one is just due to thermal expansion. So this is just due to the heat, which is, I think, the larger component compared to salt.
Some have the impression that this diagram up to 2100 looks rather different to the tar. I remember there's a sea level development in the tar for the different scenarios were not that different. They ended up at something of 40 centimeters or so, or let's say 30. I mean, only the thermal part at 2100. So you are, first of all, they diverge relatively strongly, and they also have a different level, right?
Yes, they do.
So it's only half of it.
You would know much more about the third response, the third report than I would. You know much more about the third report.
No, just remember this diagram. All people are using it.
Yeah.
So I noticed that it's markedly different.
Right. So there's a difference. One of the things to point out here is there's a difference between predicting what the atmospheric temperatures are going to say and what the sea level does. That if you reduce CO2 levels now, the temperature will respond reasonably quickly. The sea level, you're still going to have commitments to. So Florida is, yes?
The tar sea level runs were not tied to SRES scenarios.
But this was this wiggly shock tar.
Yeah, but the tar didn't, when it reported what it reported, it wasn't reporting assessments of literature that ran sea level rise off of SRES scenarios. They were only about 6 months old at the time the tar was released.
I'm just saying what is published. There are sea
But you
level
mentioned
scenarios, A1, B1, blah, blah, blah.
Okay, you mentioned the tar.
Yeah.
The S1, B1 business wasn't in the tar. It was.
Okay,
So
with
with
the
the
time.
yeah, with the it was. But actually, I think the range is similar to the tar. Because the target's like 30 to 80 or something. The range.
No, I mean, if you just take the thermal expansion, and I use that diagram, there are, it's a diagram which says the expected temperature and the sea level increase according to scenario A2, B2, and these type of things. It's nothing new. They are all of the order of 40 centimeters, say 30 centimeters at the end of this century, and they're all relatively similar. And I think this went through the wiggling machine.
Didn't have this offline. Yeah. But nevertheless, I mean, that's what Tar said.
And it also diverges a little. We're worried about that.
Okay. So we're going to have a quick summary for that. These aren't conclusions yet, so this is just a summary so far. Just in case you're getting ready for your afternoon break. So what these models say, and I've shown just from one, but I think this goes across this class of comprehensive climate models, is gradual changes in anthropogenic forcing produce gradual changes in the North Atlantic overturning. There are THC reductions, but by my definition, these are not collapses. Collapse means it goes down to something that 10% or less. That's going to be my definition of collapse. Now, as I said, I put forward this other measure of thermohaline circulation about what gets subducted down from the deep water formations. But the interesting thing about these models is that the percentage reductions in that are almost exactly the same as the percentage reductions in the North Atlantic overturning circulation. And that result I cannot explain. I do not know why those two are similarly related.
Apropos of the previous discussion, what happens to the wind stress over the Atlantic?
The wind stress modifies some slightly, but not very much during these changes. Yeah, that obviously changes more than the wind stress itself.
Could it be that it's controlling?
Yes. So if you just had to say that, therefore, both those measures are controlled by the same mechanism, clearly the Gulf Stream is controlled by the curl of the wind stress. So therefore, you would put down to be that the amount of deep water formation is also done by the curl of the wind stress. That's a logical and interesting conclusion.
The other question is, what happens to ice cover?
I will.
You
I hope I'm coming to that. But it obviously retreats and whatever. So, this THC strength appears to be relatively simply related to the stability of the column and how much heat you start putting into it. That, again, was a result that I disbelieved for a long time, but it does seem a really relatively simple explanation. So, this is what we were just talking about. This is true for the deep water formation regions and that water that's formed, and in the overall North Atlantic MOC. So, hold on a second. The next question I wanted to ask is, what the heck does these reductions do to the temperatures in Europe? Now, so I was surprised to find that in my local, my favorite paper, which, I'm from England originally, so this is the weekly airmail edition from the Guardian Weekly in February of this year, would tell me that global warming is going to freeze out the British Isles. So that's what I heard, and I hold on, stop reading down yet. This was meant to be an abrupt surprise for the organizer of this meeting, because as you can see, the person that they quote most here is actually Michael Schlesinger, who talks about the chances of the Gulf Stream reducing, and he calls it collapses here, with a 3-degree temperature rise. But these two guys can't get away from here. From here are figures from the Hadley Center for Climate Change, given at the meeting, showed that in some places, the North Atlantic, the temperature might drop as much as 10 degrees centigrade, and over the UK by 5 degrees centigrade. Now,
If there hadn't been free industrial code.
now, okay.
Sorry.
So, the Hadley Center gets its chance in the response.
I think there's a little sensitivity in the audience.
I mean, what's written is not
Play nicely, boys.
Well, one of the things I'm really interested about this article is, the other one, of course, says that why are you going to get, instead of fish and chips, which is the traditional English one, you're going to get jellyfish and chips. The reason for that is that the North Sea is going to warm up so quickly that all the cod are going to go farther north, and you're going to get jellyfish in the North Sea. So the two aspects of this report are...
Couldn't they go back west to Canada?
The two aspects of this report are sort of entirely contradictory. One saying that it's going to get really much colder, and the other saying, as well as acidification, it's going to get much warmer.
Like the halt of the Gulf Stream.
Yeah. Stop. It's the old Canute stop. Anyway, I thought this had a sort of interesting thing, and especially with these participants, and I already had looked at the participant list for this meeting. I thought this was something to bring. But I think it does raise issues about, the reporting of this material. This report has obviously gone for the most sensational parts of the meeting that was held. And there's a whole sort of spectrum of views, and that the reporters sort of go for the real extremes, it seems to me, and not for the mainstream results. That was The Guardian, not Science. So, the real result about what happens to Europe's temperature in these scenario runs is that the temperature goes up in all of them. This is the 20th century commitment. Actually, the only region where it actually goes down is just this little area here, and it goes down, and in the scenario runs, the temperatures all go up. As usual with everything, it goes up more in the northern hemisphere than the south. But basically, at the end of the 21st century, surface air temperature consistently warms in all these scenarios. And so, the rationale for that is that you're warming a little here, but the THC only goes down just a little, so the warming wins out. As you up the ante of the scenarios, the THC decreases more, but the warming rate is actually faster. No, because you have real changes in albedo of ice and whatever there. These actually, they are larger than other models. But basically, the answer to is it's not going to freeze out Britain, because if you believe these models, every scenario you run, the temperature is actually going to increase. So, are there any abrupt transitions in these scenarios that we've looked at? And the only one we found is in one of the A1B scenarios, there is an abrupt change, and it's due to the area of sea ice. This goes from 1900 to 2000, and right at the turn of the century, there's one fairly abrupt change, stabilizes again, and then it goes down again. Now, this actually is labeled just September to make it look more dramatic. What happens is that the ice comes back some in October. So if you actually look at a fall average, it's not so good. But we're after abrupt changes here. So this is the best we can come up with, and you've got to massage your data to make it look abrupt, or else I won't get invited back. Anyway, in all other scenarios, such an abrupt change as this doesn't happen. And what I'm going to show you now are the sea ice extents in the Arctic for that, and these areas. So let's go ahead.
Which scenario?
It's A1B. So that's one from 275 up to 750 and 2100. So this is the ice concentration in the Arctic in September. Present day sort of values, with much more ice over against Canada. And as you can see, it mostly completely fills the Arctic. The next one, after that first abrupt transition, it's going down. Start to get ice-free areas, just in more areas like that. And in the last one, where you've really dropped the sea ice a lot, then you've only got concentrations against Canada, and all the black areas here, you have no sea ice at all. In the A1B scenario, you go to if you believe these, you go to a time around 2060 where the summer sea ice has gone in the Arctic. And if you press it again, a little boat is supposed to appear here, showing that that is in fact open water. But I think that, you know, if you believe these strong scenarios, I mean, polar bears are in a lot of trouble over the next 100 years. You know, they're already in trouble. That there's one population which breeds in Hudson's Bay, and when it melts, they come onto land. They come on and essentially don't eat anything for about 4 or 5 months. And then they wait for Hudson's Bay to freeze over before they go out. If you ever want to see polar bears, go to Churchill in October, soon to be early November, because it's freezing later and later. But that population is believed to be in trouble because that time they have to spend on land is getting longer and longer, and it means they can't get enough food for the females to be able to reproduce successfully. But I mean, polar bears are maybe an endangered species. So the way we can get real abrupt changes in sea ice is to really abruptly force the ocean and to change the overturning circulation. So these are results from Villinger and Wood, Villinger et al. Why don't you tell me what you did to the initial condition to start these experiments?
What we did, we took a salinity profile from the North Pacific and transplanted it over into the North Atlantic, with the North Pacific being much fresher than the North Atlantic. That then resulted in a really fresh North Atlantic. As a result, we suppressed the deep water formation and wiped out the density gradient that drives the overturning circulation.
In a large area of the North Atlantic, the salinity went down by 2 parts per thousand over the upper 800 meters, something like that. So that's a huge change. It clobbers the MOC. And in this case, you get up to 10-degree changes in the North Atlantic and 5-degree changes off the thing. So I think that Guardian reporter was asleep until this result got presented at the meeting, which is where I think the 10 and the 5 came from. Pardon?
The North Sea result, where's that coming from?
He fell asleep again.
That actually came mostly from the acidification of the ocean report, I think, on that. You know, every group's done this sort of thing. If you really hit the North Atlantic with fresh water, you can make it collapse. These are values where this was actually with the earlier version. If you hit it with a 0.1 sphere drop per year for several years, it goes down somewhat and recovers. If you really hit it with a lot of fresh water, then 3 compared to 16 I will define as a collapse.
Peter,
But then it comes back.
you guess how much the wind stress changes in those runs?
Some, but well, what about in your runs?
It changes, but not much.
Yeah.
It's
Okay.
not just, this is not just a wind driven circulation.
Right. But the wind doesn't change. But I mean, once you allow time so that you sort of the circulation gets back into equilibrium, I mean, you are going to get back in the end, I believe, to the same value up here. So if the wind stress hasn't changed, once in your equilibrium, I don't think that really counters the argument that Carl likes to make about that it's the wind that's doing everything. But clearly, if you make abrupt changes to the overturning, you can get abrupt changes, and they will cool Europe. This is the temperature change from those experiments I just said, and again, this is the 0.1 sphere up, the 1 sphere up, but note that the scales are different. This is 3, this is 16, and again, much of the northern hemisphere, including the ocean. And it's clear that a lot of those changes are because the sea ice extends. In these, you cut off that northward transport, the sea ice expands, the surface air above the sea ice really, really cools. So I believe that if you have these abrupt changes, sea ice has got to be involved. The changes in sea ice might be forced by changes in ocean or circulation or atmosphere, but there's no doubt sea ices are positive feedbacks And if you're going to these abrupt changes, I believe sea ice has to be involved.
That's a question from wind stress.
Exactly as well. If you go from open ocean to sea ice, the stress that where the ocean seas changes is a lot. Okay, conclusions. THC reductions occur, may, due to anthropogenic forcing. These simulations, or Europe always warms in future scenarios. I've only looked at a few of these, but last week I asked Jerry Meal whether that was right, because he's looked at many, many more of that, and he says that is correct. There's one member of the A1B ensemble where we see some abrupt sea ice changes. We're going to look at that a lot more carefully to see what was going on.
So I didn't understand, how many A1Bs did you have?
6, I believe.
But it happened only in one.
That was that strong only in one. Abrupt change overturning circulations are caused by abrupt freshwater additions in the North Atlantic, and Europe most often cools in these experiments. Thank you. Questions?
Two questions. Can you comment on the Seeger, the statistic paper?
No.
You probably could.
This is the paper where they claim that the climate of Northern Europe is set much more by the Rockies, making the Northern Hemisphere winds go north over the Rockies, down, and then back up, rather than the overturning circulation bringing heat up. What you'd actually need to check is exactly what's happened to those wind changes, but I believe those are going to be less than the overturning circulation changes. So that would produce less credence. A statement on the other side is, by the time you do get to the latitudes of Europe and Britain, the amount of heat that the MOC takes north is a lot less than the 1.2 at 23, 24 north.
Yeah, the second part of the question is related to the things I spoke about, that these models, especially in the North Atlantic or high latitudes, there are two possible impacts, and the partitioning between them depends on some parameters. These models seem to favor the thermohaline.
Yeah.
So the fact that the winds didn't change and so on is just another reflection of it. Yeah. It's conceivable as some other model where the thermohaline would be quite secondary. All the changes would be the winds.
So we're looking forward to you producing this model in the near future, George?
Well, I'm taking the argument, I've tried very hard anyway.
So in that model, is it true to say if you did this freshwater hosing experiment, you wouldn't see any difference in the climate?
No, I'm saying alternative. I'm showing you how the higher CO2 versus the IPCC models do not change gradients long term. The gradients stay the same. I can envision a world where that's quite different, where those gradients would change. And then you'd have quite a different response.
Hans.
I have now this diagram here, which is supposedly not existing. It says A1B, A2, B1, B2, 99 to 2100, and I have it from the IPCC.
Yeah, it's working group 1.
That's the solid one, right? There's a solid of the working groups, I would say. And I have here a diagram saying, so all the different scenarios here, they have a best guess or something, I'm not sure what it is. Maybe it's a mean value or so. And they end up at the end of the century all at about 40 centimeters, maybe the green curve that's B1 and 30. Then they have a gray band indicating likely something like uncertainty, and that varies from 20 to 22, let's get to 60, 65 centimeters, just thermal effect. That would mean your curve is really at the lowest end of that. Is that, I mean, is that now an outsider for the next report, or is it a?
No, I think that you know,
it's a revision of the estimate.
How much heat goes in is really mostly dictated by the climate sensitivity, and our model is on the. It's not on the low end, but it's below the median. So.
Yeah, but here it's even. I mean, it's really almost. No, it is outside. I mean, if I go for you had one, the B1 or B2, what do you have?
Yeah, but remember that that diagram needs to be corrected for the control as well. So I think it would go.
So you
Those
think
numbers would
you
go
get
up.
10 centimeters extra?
Yeah. Yeah.
So we don't need to revise the wisdom work group 1 of the third assessment.
I'm going to make absolutely no comment on that.
That was a loaded question.
But I was not involved with that.
No, it is just, I mean, this is just reviewing what is out of the literature.
So please do take it.
Okay. Could I ask you a question? Do you know, can you say anything about changes in precipitation patterns over land?
I could.
But I mean,
I didn't bring any of that.
Yeah.
The other thing that's absolutely consistent among these models is in a warmer world, the throughput of the evaporation precipitation cycle increases.
Yes.
And again, depending on your climate sensitivity, is the rate at which that increases. In our model, that increases by something like 4%. And that then will depend on the scenario. The precipitation patterns change quite a bit. And then, of course, the other question that's always asked is, with that excess evaporation and precipitation, how is that precipitation going to come down? Is it going to come down, as the gentle rain from heaven, or is it going to come down as more extreme events? That is a real question. But I don't think these models are going to.
So, but if you want to worry about scary scenarios, it seems to me drop of temperature in England is not nearly as scary as the sort of changes we've been seeing in precipitation.
Have we been seeing real changes?
Well, droughts, and what's going on today.
Again, that's very hard to say what a secular change is given the large innate variability.